Okay, here is our last video of the summer. It's on lesson 14.5. It again includes discussion about limits, this time limits involving infinity. The two big ideas in this lesson I hope you kind of could gather from doing the reading and doing the guided reading notes is when the limit is equal to infinity, which is kind of a wrong way of saying it because in this case we really, for convenience purposes, we describe the behavior of a function using the notion of infinity. But in that case the limit doesn't exist, we just say the limit is equal to infinity. The second case is when the limit as x approaches infinity, so we look at values of x that get further and further away from the origin. And that can either be equal to a real number when we have a horizontal asymptote, or it could be equal to, we state, infinity. So let's first look at the first case, the limit when the limit is infinity. Additional example 2 has this function and talks about describing the behavior of the function. Again, notice, we're not going to find the limit. We will use limit notation to describe the behavior of the function. But they'll describe the behavior of the function, this rational function with -5 as a numerator, x squared minus x minus 6 as a denominator, near x is equal to 3. You might recall from your study in Algebra 2 and in pre-calculus, it would be wise probably to look at the factored form of the denominator. And if you factor the denominator, it appears it'll give us some information. Also, some of you might be anxious to get a quick look at this function on your graphing calculator. So if we look at both results, here is the factored form of the denominator. Here is what you'll see on your calculator with this window, -4.7 to 4.7 in x, and -3.1 to 3.1 in y. And if you don't use the zoom decimal form, or you don't put where the asymptotes are as the middle of your screen, you won't really get a picture of it like this. Your graph will kind of show the vertical asymptotes existing, or some connection between down here and up here. So recall, algebraically, there's no doubt that we have no values existing on this function when x is 3 and when x is -2. Consistent with the graph, here's -2, here's 3. They're vertical asymptotes. And what happens a lot with rational functions is we might get vertical asymptotes. So in this case you can see that as we get closer and closer to 3 from the left, where the graph is increasing without bound, if we approach 3 from the right, it's decreasing without bound. So to describe the behavior of the function near x equals 3, we would make these two statements. We'd use limit notation, although the limit doesn't exist at 3, nor does it exist at -2. We can still describe the behavior of the function by stating that as you get closer and closer to 3 from the left, the values of the function are increasing without bound. If you get closer and closer to 3 from the right, the values of the function are decreasing without bound, consistent with the graph. So once again, the limit doesn't exist at 3, but we can write and describe the behavior of the function by using limit notation. Now let's take a look at what happens when we look at functions and examine the behavior as x gets larger and larger, and we say as x approaches infinity. Once again, notice the directions for this question. Additional example 3 to say to describe the behavior of the function 1 over x minus 3 as x approaches infinity, as x approaches -infinity. Once again, there seems to be no value at x equals 3 because that makes the denominator equal to 0. We might be able to picture in our mind what this function looks like. If not, with this window, here's what we have. We have our vertical asymptote at x equals 3. But in this case, we're not looking for what the behavior of the function is around 3. We're looking for the behavior of the function as x approaches infinity and -infinity. So we're tracing along this curve as x gets larger and larger and larger, and as x gets smaller and smaller and smaller. What are the values? What's the behavior of the function? Well, as we know, when we have a degree of the numerator smaller than the degree of the denominator, we're going to have a horizontal asymptote, and that horizontal asymptote will exist when y is equal to 0. That's exactly what we have here. So how do we use our limit notation to describe it? We'd say the limit of in this case I'll use the f of x instead of this. The limit of f of x as x approaches infinity is 0, as is the limit of the function as x approaches negative infinity. So again, in this case, the limit does exist because our value is 0, and we say, using our properties of using the limits at infinity that you can find on page 951, and I did not have you jot that down, but basically what we're saying is that this value 0 is our L, and as x takes on larger and larger positive values, increasing without bound, the corresponding values of the function get very close and possibly are equal to a single number L. Well, in this case, they don't actually equal 0, but the second part of that limits at infinity theorem says that the values of the function can be made arbitrarily close as we want to, by taking large enough values of x. So I hope you agree with me that however close you would want me to get to 0 along this function, maybe right here the value of the function is 0.2. You say, well, I want you to be closer to that. And I say, fine, I will just continue to go out further. I'm claiming, and I think you'd agree, I could find a value. I could find a large enough value that will make this function take on values close enough to 0 that you set as the standard. Now with polynomial functions, and here we have an odd polynomial function with a negative leading coefficient. Think back on our study of behavior of functions, polynomial functions. You might remember that odd functions start low and end high, but when the leading coefficient is negative, they start high and end low. That's what the behavior looks like. In between, we don't really concern ourselves because we're describing the behavior of this as x approaches infinity and negative infinity. So you could take a look at this graph, but looking at it with this window, which is all we need. In fact, some people would claim they don't even need to do that after what I just described about the behavior of the end behavior of the function. You can see clearly that as x approaches, as we get smaller and smaller values of x, we're getting increasing values without bound. As we get larger and larger values of x, we're decreasing without bound, which is consistent with how we pictured this function. So big news is the limits do not exist. However, we can describe the behavior of the function this way. We actually use the infinity symbol, and as you recall, or we use negative infinity, infinity, and as you recall at the beginning of the lesson, that first sentence that's really stated that there's no real number called infinity, and the symbol infinity, which usually is read infinity, does not represent any real number. So we're kind of using, as mathematicians are famous for, we're kind of trying to find a shortcut way of describing behavior. We could use words for this, but this symbol, we're kind of breaking the rules a little bit, using symbols that imply that there is a value for the limit. And there is no value for the limit. Limit does not exist. Whenever you use infinity to describe a limiting value, you're stating it doesn't exist, but you're describing the behavior of the function. Okay, now, example 5 and example 6, as I implied, talk a little bit about kind of long, detailed solutions, almost proofs that kind of show how the function, how the limit is arrived at. So we look at this one. This is what's found in your book on page 955. And what I want to say is, if we start here and divide by the largest power of x found in either, and we use some algebra to get it down to, say, this point right here, then the rest of this I don't think needs to be documented. So you start here and you'd say, well, look, the limit of the numerator is 3 minus 0 plus 0, which really comes out because of these properties that allow us to break up the limit of a sum into the sum of the limits. Same with the denominator. So at this point here, or maybe here, you could realize that the limit of the numerator is 3, the limit of the denominator is 2, thus 3/2. So the documentation up to here would be something kind of in this area. So getting down algebraically, showing me you understand the process would be real important. When it comes to this one, similarly to example 6 in the book, the limit is found by dividing both numerator and denominator by x. However, when you divide by x, the numerator and denominator, or as the authors say, multiplying by 1 over x, you treat the numerator different because it involves a radical. So we're going to express x as the square root of x squared, because if x is greater than 0, which is the case we're looking at now, we're only looking when x is approaching infinity, we're only looking for values of x that are greater than 0. We can express it that way. Here we'll leave it as in the form x. Clean up, and now again we can get to a point where we can say, well, the limit of the numerator as x approaches infinity, since this is getting smaller and smaller because of the limit theorem, again refer to the limit theorem on 954, as 1 over x squared as x squared gets larger, 1 over x squared gets smaller and smaller. So this is approaching the square root of 2, this is approaching -5, and thus the quotient is approaching the opposite of, or negative square root of 2 over 5. Not something you'd probably find with your calculator. Now you can verify this with your graph and see that there is indeed, should appear to be a horizontal asymptote at negative radical 2 over 5, or the decimal equivalent of that. But finding that, as we all know, with our calculator, converting that irrational number written in rational form back to the radical form, it just can't be done with our TA 83s and 84s. So again, getting to a point where we can evaluate both the numerator and denominator's limit would be good enough as far as I'm concerned, as long as we can come up with the exact answer, which is shown. In this case, the limit does exist because we're not using infinity to describe it. So that brings the end to our video lessons and much of your work. You still have 1 through 36 to do on page 957. That's assignment P. This will be your last written assignment. Actually, you'll submit your even numbered answers on the forms. Odd answers, check in the back of the book. If you have any questions, email me. And remember that assignment Q, that review assignment, that will be something we'll kind of start the year off, kind of bringing all these ideas of limits and continuity together. I hope you've had a fairly successful experience using the video lessons and the guided reading assignments, along reading the textbooks and doing the homework assignments. It has been a trying summer, I know, because no one wants to do pre-calculus, especially study with limits during the summer. Thank you for your efforts, and we'll see you at the beginning of September, and we'll get all this worked out.